In this module, we'll try to cover some of the data modeling techniques. It's a vast topic, and we'll see if we can do justice in the time allocated. And start with my first slide from this morning, re-emphasizing we're a record-centric database. So all your modeling has to be record-based, right? So given that, among all the choices you have, and if you're coming from the relational world, as I spoke this morning, you're used to thinking in terms of tables and relationships and entering data only once in any given table and then running your queries by joining the tables in the database. Unfortunately, NoSQL databases and Aerospike in particular don't have the concept of tables or doing joins for you in the server. So you have to encapsulate your data at the record level. So you have records and you look at the queries you want to run on your data and design your data model so whatever you need is encapsulated in the record itself. So I have this example of folks taking trainings. So you have employee ID and the trainings that are delivered on a certain date, and then you keep track of which employee took which training. In the relational world, the entries will be only one entry, one piece of information per table. In the NoSQL world, if I want to list all the trainings for a particular user, I want to be able to go to the employee record and pull this map of every training that he took on which date. Likewise, if I want to know who is registered for the current training, then I'll go to the training record and get a list of all the participants. Now, what does that mean in terms of maintaining our data? That means when I announce a training and I have 20 registrants, I have to update this record with the registrant IDs. And then when they successfully complete the training, I have to go update the 20 records, individual users. So right off the bat, I've made it a multi-record data model, right? So you're updating 21 records just to do this. So keep that in mind. Even though we're just a record level lock database, now you're separating it into 21 transactions. And the consistency is up to the application. Aerospike will not maintain consistency and say, hey, here are the 21 records, go update them simultaneously. No, that doesn't happen, right? So we're just doing it at a record level. So from a data modeling perspective, you have to ask yourself, am I building a multi-record transaction? So before you jump into modeling your data, you know you are at Aerospike because you want speed at scale. You have to ask yourself, do I need consistency, the strongly consistent model, or do you are okay with AP? So we went through AP and SC differences, especially those who attended the SC class last session, that you have to make a choice which way you want to go, and do you need multi-record transactions? Got to know your traffic and your data, obviously. What kind of SLA are you trying to achieve? And then even for a simple key value lookup model, you can greatly optimize to reduce your TCO. And Tim talked about those things, right? The all-flash model, where by selecting the right namespace, you can save a bunch of dough, right? So even if you're doing a simple key value lookup, there are options to consider and talk to us about. And then you have to look into, do I need secondary indexes? And in the first talk, I talked about how secondary indexes run on all the nodes of a cluster. And so you may want to consider fail on cluster change option, or you may want to ignore it, depending on what you're doing it. But you have to understand the limitations of scans and secondary indexes, because they just are sent to the nodes and they run for a long time, and whatever happens in terms of the cluster change, you get what you get. But if you want deterministic behavior, then you have to stick to record level operations. Okay? And then how do you denormalize your data to address the queries you're interested in? But in the final analysis, really data modeling is tightly coupled with your total cost of operations. That's why most of our customers start with data modeling. When they decide to use Aerospike, the first thing is they engage with Tim and his team, and we go through the data model. And really, it is all about cost. because there are many ways to skin a cat, and the right way will get you the lowest cost. So with that said, let's look at some of the decisions you take about modeling specific to Aerospike based on the Aerospike architecture. The first thing you're going to decide is what namespace you're going to use. We talked about these 4 options, and now we have index in the Intel Optane PMEM also. But leaving PMEM aside, we have hybrid memory model, which gives you the fastest latency performance with persistence. You have the all-RAM model, as Tim mentioned, that's for really smaller data sizes. Your cost will grow up if you try to do everything in on-RAM for a large data set, but it will give you the fastest performance. And then you're dealing with possible data loss if you lose replication factor of number of nodes simultaneously. Then, of course, you have the all-flash model, and that's a very compelling model to consider if you have very small record sizes. And then you have the file system-based situation where I know there are some folks who are doing file system-based even on SSDs because they feel they can do backups a lot easily on the file system. And it's good for a small data size again because you're keeping a copy in RAM for performance, and then you're using a file system for backup. So I don't know if folks from those who are doing here are here or not. I don't see Atreya here, but he's the culprit. All right. So let's go to API-based features in data modeling. Some of the things to consider. Gen equal in the write policy is something often used if you want to do read, modify, write. So as I said, we have a record level lock. A read is a separate lock from a write on the same record. So if you want to read some data, come back to the client and modify it, there is always a possibility between that gap, somebody else came and modified the record. So using the gen equal policy not only reads the data, it'll read the generation of that record. And when you write, you say, hey, update the record if the generation is still the same. And if it is not, come back to me, I will repeat my operation. So that's a good technique to kind of employ where you're worried about read, modify, write. The other option is to use record UDFs, but they have a performance penalty and they're slower. So I would recommend gen equal over record UDFs. So in a UDF, you are giving the server a user-defined function and building all the logic in the function itself rather than come to the client, because when you're doing a read, you're doing some kind of a logic based on what you read and doing an update. Now you can program that all in a UDF and have it run on the node itself, but there are limitations with UDF, which if I get to the last slide, I'll cover. Write policy flags such as update only, like don't create this record if it exists. That's an interesting technique that is used in making sure that you're creating only a unique record, and some data models will exploit that. In complex data types, we have maps and lists, which offer a very rich set of APIs. And I'll go through those today. Then we have this interesting flag in maps called create only for a key, which means don't create it if it exists. And that is very effectively used as a record level locking mechanism, which I'll show you towards the end of the presentation on doing a multi-record model. Finally, I want to point out operate command in our APIs. The good thing about operate is you can stack a bunch of updates you want to do the record in the same lock, but you get a free read on the way back. So in the same lock, you can do an update and read back. You can also do reads through the operations if you want. So you can get what it was, what did I change to, and what the final value is. You can get a whole array of reads back from each operation as well. Okay. So that's very powerful. And of course, the other things are secondary index queries, scans, and then predicate filtering is also quite powerful, especially if you're doing filtering based on the record metadata, because that's in RAM, right? And any predicate filtering working on the primary index, like last update time, if you want to do any filtering based on that, that's pretty handy. All right, on maps and lists, they are basically key value pairs and they can be nested. So against a key, I have another map here, and this is called a nested map. And what's coming soon, I believe in a couple of months, you should have access to the nested maps also through our map APIs. Which means currently, if I want to update, say, this particular value, which is a nested map inside Y2, the value for Z1, I have to send the whole Z1 through the whole submap, right? I cannot individually update it. But once we have this in a couple of months, you can do that, right? So that's coming soon. That'll make maps even more powerful. And then the only thing you have to know that if you are using time to live on a record, then that's at the record level. It doesn't translate it at the map key level, right? So the whole record has a time to live. It's not by key value pairs. And other limitation with maps is currently the UDFs have a very limited ability to modify the maps. The rich set of APIs that are available at the client level are not fully available at the UDF level. And anyway, I discourage you from using UDFs if you can, if you want performance. Now, in terms of some of the terms that need to understand about maps, so I can explain you the APIs. The size of a map just gives you the number of KV pairs. Index is the position in the key value pair, pairs in the map, right? So anytime you insert a key value pair in a map, it is inserted in the key order, always, right? So if I had 1, 5, 6, and 7 as my keys and I inserted 3, it'll come over here. So its index position will be 1. So they're always inserted in key order. You have negative indexing available, so you have 0, and if the size is, so -1 would be this value. Now that helps us a lot. Negative indexing is very powerful, right? And then we have rank available, which is the order of the value part of the map, key value pair. So if I say, give me rank -1, I get the maximum value in the map. So you see the power of the APIs then. Once you have negative indexing and both key-based search, index-based search, and the rank-based search, all three. On the list, you have, again, the index, again, the negative index available, and the rank by the value. Now, lists, unless you define ordered, it is by insert order, whatever you inserted. And then if you want them sorted, you can also do no duplicates. So you have options there with lists too. Okay. So then let's look at the APIs. Besides adding the items and incrementing and decrementing them, you can get or remove by key, by index, by rank. You can again get or remove by the key interval, the index range, the value interval, the rank range, all by value, all by key list, all by value list. So very rich set of APIs that let you do some very interesting data modeling. And likewise, you have the same set available with lists. So these kind of APIs, these are not available at the UDF level. You can still modify individual items and such with UDFs, but this kind of rich set is not available. Okay. So that was like a little bit of primer on the, what is available from a Aerospike architecture point of view. So given that, and since I'm not in the presentation mode, I've lost my timer. So you guys will tell me when I'm really running over time. Let's look at some of the modeling tips. The first thing that you will find you use often is composite keys. And composite keys basically allow you to break a record into multiple records. For example, if I was storing for a user by every day the list of URLs they visited as a key value pair, at some point you'll hit the maximum record size in Aerospike. So if you are most generous and used our maximum, which is 8 megabytes or mebibytes rather, you're going to run out of space. So how do you deal with it? Well, can I generate a composite key that is intuitive to the application or algorithmically predictable to the algorithm, to the application? So I want to go break by day. So that way I can figure out the composite key for any particular day that I'm interested in, and then I can just store the list of URLs visited, assuming that will fit in my 8 megabytes. Okay? So that's the idea behind composite keys. You explode the number of records, so you're paying price in terms of primary index, so you do it when it makes sense. Okay? If you overdo it, then of course your RAM will blow up. So we'll look into those kind of things as well. So you have to use it carefully because you're exploding the record and you're losing the record level atomicity. So here you had a single record, so everything you did was in one lock. Once you break it into multiple records, the idea is you're only updating one particular record, the other one doesn't matter, right? So if I update the URL visited today, I don't really care to update those. So that's perfectly fine to do that. So always remember the record level lock in Aerospike when you do your data model. Okay. Composite keys and counting on the fly. So here I'm presenting you a problem that I want to count every time a particular user sees an ad Y. And somebody, I think you were asking me this morning about the same use case, right? And you want to provide a list of all the unique users who have seen this particular ad. And then you also want to know how many times a particular user has seen. So if I use a composite key with user ID and ad ID, right? And then I also note down the user and I also note the ad. So every time a user sees this ad, I'll bump this count. So that's my aggregation on the fly. Now how do I find the exact, the unique users? I can run a secondary index query on the ad ID and pick up the users. So I'll get all the unique users who saw this ad. So it'll use secondary indexes as well as counting on the fly. So that's, and composite keys, okay? Hash, this is again a very powerful technique for really reducing your cost. So here the problem is, I want to do a reverse lookup. I have a user and I have some data about the user, and then I have some attributes about the user, like his email, phone number, whatever, zip code. And I want to be able to, well, not zip code, it has to be unique to the user. So let's stick with email and phone number. If I have the phone number, I want to be able to find the user so I can go get his data. That's the reverse lookup problem, right? So what can I do? Well, I can build a whole bunch of records that tie back the phone number to a user, small records. So I'll go first look up the phone number, find the user ID, then come in second time, go look up the user, right? That's one way to do it. Build a lookup table. The other thing is I could build a secondary index on the phone number. And I can then query the secondary index, hey, give me that particular record, and I can go find my data. So there's two ways to do it. Well, that maintains the record level atomicity, but both are bad. So let's see what happens. If I do a lookup table, if I have 1 billion records and each has 2 attributes, email and phone number, if you do the math, you'll find you'll need about 119 GB of RAM to do the reverse lookup table, a whole bunch of records that map the phone number back to the user ID and the email back to the user ID. Likewise, if you did a secondary index on the user attribute and go through our sizing sheet, it'll tell you the SI requirement will be about 119 GB in RAM. It's basically building the index in RAM. What if I hashed my attribute and decided the number of bits to keep based on the compression I want? So I take a RIPE-MD160 hash of this email, and then in this example I'm just using 26 bits. And I'm using that as a primary key. Okay? So once you give me a phone number, I'm going to compute its hash, look at the 26 bits of the LSBs of that hash, and against that I'll have a record which will list me against the email every user ID and phone every user ID. So now what is happening is a whole bunch of different records will end up in this hash depending on the hash, right? But I got a reverse lookup table with a 30x compression. So instead of dealing with very small records, each individually pointing to a user ID, I have put them all as a key value pair, and I can size my number of bits according to the compression I want to achieve and how much I expect the data in this record, so it doesn't overflow. So this ends up solving the problem with just 4 GB of RAM. So that's the point I want to make. Data modeling is about saving cost. So that's, and one of our customers has implemented it. They are currently using that in production. Is that right, Tim? Okay. So how do you do then? Because remember, now you're back in a multi-record situation. You're doing a lookup in a different record and then going to another record. So how do you maintain consistency? So if you follow a sequence of operations, then you would avoid hung pointers. So that's what they have come up with, that if I do the update the lookup table entry first and then go update the user ID, and then if I'm doing deletions, deal with those last, then you stay in an acceptable state. So anytime you end up in a multi-record transaction, you have to think about, what if I updated one and I died, right? After I created the entry, but I didn't update the user ID, what happens? So yeah, you'll end up going looking something and not finding. But that's okay. You don't want a situation where you updated the user ID, created a phone number, and then died, never updated the lookup table. Now, every time I look up for the phone number, I can't find it. So that's the kind of choice you have to make, logically thinking through with every failure condition and timeouts that may happen in the client. What will you do? If the client dies, what would you do? Will it be in an inconsistent state? Okay. Of course, you reduce the TCO. Now, this was before we introduced all flash. With all flash option, you can do the small record look back. So that's also cost effective now with all flash. Because really, the cost is where? The cost is right here, right? So if you went all flash, then that goes away. So that's option number 2 available now. So that was the reason why all flash actually came about. A lot of customers demanded that. Hey, can you do this? Same technique, let's say if I'm modeling very small, tiny objects, very small number of objects. I have just a primary key with very small data, and I'm consuming a lot of RAM just in the primary index. My data size is very small. It's comparable to the primary index RAM. I can take all those records and stick them as key value pairs against a key that I generate to the hash. So how do we do this? Well, I'll take the user ID and I'll hash it, and I'll pick the number of bits to keep as the primary key. So in this example, I show you with the 256 unique keys, I can compress them down to 8 records. Okay. So anytime I want to see ID 1 data, I'll hash it. I'll look at the 3 LSBs, and that'll be the primary key in which I'll find my record. Okay. So again, this is now a single record lookup, right, and update, but it has its challenge in terms of now you have multiple records sitting inside a single record. So XDR, if you're using, is no longer shipping individual records, and you lose the record level time to live if you're using that. So if you're using live forever, then you're good, but you lost the granularity if you're using time to live on individual records. So that's what you lose, but you significantly save money. Okay, so nothing is for free, but you get something for sacrificing something else. So let's move on to these multi-record transactions. It's something I wanted to touch because this is very interesting. Multi-record transactions, the way to implement it is really you have to make your records stateful. It all has to be done at the application level. They are not offered at the server level. So please don't take away from this as I'm saying Aerospike can do multi-record transactions. Aerospike can only do record levels transactions. But in an application, you can build in the logic to do multi-record transactions with our strong consistency mode of operation. Because for any of these schemes to work, you cannot have split brains, right? Those who attended the first talk or the SC talk, and I'll kind of revisit this issue. So in strong consistency mode, successful writes or updates are never lost. Successful, right? So you guys, what you were talking to me earlier were unsuccessful writes. But if it is successful, it's never lost. You can configure the reads to be never stale, and you never get dirty reads. So with that premise in mind, we can look at how at application level you can do multi-record transactions using cooperative locking. And to implement cooperative locking, we'll use things like the map create only flag on the keys, right? And in this scheme that I'm proposing, I'm going to use a UDF, and then the follow-on example, we'll do it without the UDF. Okay. So let's revisit split brain, where you have a cluster, say in AP mode, it splits into 2 subclusters, and each kind of takes in data as if it's a master. So when you do that, this guy is behaving, he's got the master replica and he gives a valid transaction, but this doesn't have the data, so either he will write a new record there if you're doing a write, or if you read, it'll say record not found. If the master and replica are on either side of the split, they'll both make copies and you'll just double your inventory. So you end up in an inconsistent state in AP mode, right? So if you want to do multi-record transactions, you can't have this stuff going on. So you have to be in the strong consistency mode, right? And then let's look at how cooperative locking can be implemented for multi-record updates. So here is my basic record that I want to update, and in it is a list of records that will be updated with it. So he's controlling all these records to be updated. Those are my multiple records that I want to update. Okay. So I'm going to say, hey, I'm doing the update, everybody stay out. So that's a flag here. So that's my flag in the record. I'm using it. And I'm going to give it some kind of a transaction ID, that this is the ID of the transaction I'm working on, and I'm updating all these records. So that tells every other client that if I can't get this flag, I should stay out till he's done. Okay. So let's see, and a big assumption here is every record that is listed here is not part of another multi-record transaction, right? It cannot be. It has to be part of just this transaction alone. So you guys with me on that? It can't be participating in some other multi-record transaction. All right, so how will this work? Well, when I go to do an update, I'll look at the in-use flag. If it is available, I'll take it, I'll increment the transaction ID, and say, okay, give me the list of records to update, and I'll start updating those. In the records, I'm maintaining 2 states. So records are stateful. This is my starting data, and this is what I'm going to. So I'm listing, the last transaction ID was 204, it had the bin value at ABC. I'm making it 304 and putting it XYZ, right? Or whatever, 344. So maybe I have updated this record, I have not updated this yet, right? So I'm maintaining the final state of what I'm updating. And so everybody knows, so George is telling me I have 5 minutes, but we have lunch after this, so if you guys are into it, we'll continue. Otherwise, give us a thunderous applause and we'll conclude. All right, so let's say we have a state in the record now. So if another client comes in and sees, hey, this record is being used, he's going to come back and retry later. So we're already like in a timer situation, right? How long should I wait? What if somebody has taken this lock and died? So that's where we use a UDF, which goes and queries the last update time of this flag. And we decide up front that it'll take me 100 milliseconds at most to update these records, right, from an application standpoint. And if that time is passed, we'll believe this is a hung transaction and we'll start unwinding it. So every client can go and unwind the transaction in parallel. And unwinding means taking the initial value and putting it in the final. So you restore the state of each record. And the first one that finishes unwinding all the records can then take the lock. So that's the basic idea behind doing multi-record transactions. So, and that'll work only with strong consistency mode. So you have to make the record stateful if you want to do this. Now, one implementation of this that we have done, I'll get to it in a minute, but I want to explain you one more technique. If you're not going to do record UDFs, then you have to poll, right? And how does polling work? So I'll give you an example for polling. Let's say I have a user who's searching for items and visiting certain sites and lives in a city. And for each of them, I want a different TTL. So I want to expire this in a day, 5 days, and 5 years. Obviously, I cannot do it at the record level, right? Because we only have one TTL at the record level. So how do I do it? I can create a map of values and a map of TTLs, which is future expiration times. And then I can go through this little algorithm using our map APIs, figure out which time is the most closest to expiration, and see if it is past my server clock, and I can go ahead and then delete both the keys from attribute and the TTL part, and keep updating my map. So I'll have to do that as a poll job and probably as a scan job running on all the records. You could do it nightly, depending on your need. You could do it every hour or so. And then on every read also, you would clean up. So that's a polling-based implementation of essentially updating your state. So in case I take a flag for in use like I showed you before, and I want to clear it by polling, I can do that too. I don't have to use a record UDF. And so in this adaptive map that we have actually written the source code for it, and we're testing through it. So if you're interested, if you have a use case for it, reach out to the boss man back there, Tim, and we can share this with you. You have an example here of a map that just keeps growing, right, beyond your 8 megabytes. How do you model this? That it self-shards and just keeps growing. And so we've taken the same approach that I just explained to you about multi-record transactions and implemented that. And here, the way it works is, if it is not yet sharded, of course you keep writing in this, and then when it's ready to be sharded, it'll split into 2 records. Now, keep in mind that here, I'm not doing any rollbacks, because I'm only appending data. So I don't need to worry about keeping the initial state and final state. Second, every record that I'm going to create is tied to this record. It's not tied to any other record. So it satisfies my second condition that all the records in the multi-record update should be tied to, should not be part of 2 separate multi-record transactions. Okay. So here's what we do. Let's say this is our basic record, and when it is full, we'll split it into 2. When any one of those is full, we'll split into 2. And then once it is split, we're going to go delete this just to recover space, right? We don't want this lying around with a copy of the data. And then how do we know when we are going to, once we have all these splits, we keep track of the splits in this record using a bitmap. So this bitmap, every time, so the least significant bit corresponds to this, the next one is this. Anytime it splits, it becomes 1. And then anything that is 0 has data if its parent is 1, right? So if the parent has split, these have data. This parent has not split, they don't have data. So that's a little logic in the bitmap. So as long as I go read record 0, I know where my data is. So let's look at how this works. For a read, again, you'll need 2 read operations once you have split, right? So first read, I'm going to read my record 0. I'll read both the data and the bitmap. Now, if the bitmap tells me this record 0 was split, that means it is as 1, I'll be able to read the bitmap and figure out which record n has my data. I can go straight to that record and read my record, the key value pair that I'm looking for. If this is 0, that means the data is still in this record. I already have the data, and I'll just read it off there. Because once this splits, I'll set this data to null also. So that's how the read works in this adaptive map. Now let's look at writes. They get a little more interesting. Okay. Let's start with the simple case of writing when the first record 0 this guy has not split yet. Okay. So I come in and I say, hey, I'll do a create only lock on the map key right here. This one is locked. And you say, hey, if it is not locked, I'll take the lock, do my key value write, and unlock. So I take the lock just to make sure that somebody else is not splitting this record. Okay. Once I've done my write, I'm going to look at I will return the size of my map once I'm done with the write in the write operation. So I use operate. Operate lets me do the return value. And then I'll see if it is over a threshold. If it is, I'm going to split this record, and I'll get into splitting how that works. Now let's say I split the record, and my record is in some record n, and I come to write. Well, once I split this record, this will always be locked. I'll leave it locked. So I'm going to fail the lock. When I fail the lock, I'm going to go and read the bitmap. And from the bitmap, I'll figure out exactly which record has my map key. I'll go to that and then do a write, again the same path for that record. Right? And then maybe when I do the write, I realize, oh, I have to split this. So then I'll go into the split. This side of the thing, if the bitmap is 0 here and the thing is locked, you have a bunch of error conditions you have run into, like timeouts and blah, blah. And we handle every one of those in this part of the deal. Okay? So you can look at the source code, it gets fairly complex there, but everything, the error conditions are handled here. Let me quickly go to the split now. Let's say I've decided a record has to be split. Okay? I'm going to read the bitmap, again, from record 0, and take the lock for the nth record, get its data, the one that I'm splitting gets its data, and if you're using TTL, then I'll get its TTL, because when I split the record, I have to maintain the TTL. So I will write it with the remaining TTL. And then you split the data by the map key hash. So now here, we're hashing the key to figure out which block it should go to. That's how it goes to a particular record. Okay? And then you'll write 2 records, then you go ahead and update the bitmap and then delete the record n if n is greater than 0. So you never delete this guy. You'll go ahead and if you're splitting this, you'll delete him. So if you follow this scheme, and if you go through this, you'll find that even if I fail anywhere in the middle, it'll still be consistent. You're not going to be left in an inconsistent state. So this is available for fun. The other option is, instead of the create only flag, in some cases we are using the key type error flag. So if you have a bin that you have declared, you're storing integers and you're doing increments, and when you want to lock the record, write a string to it. So when you try to increment, you'll get an error, bin type error. So that's another technique to essentially do these locking things. Now I'm seriously out of time, but I do want to touch on one more topic since you guys are so patient. Okay, record UDF, of course, performance sucks. So, read. Yeah. Because here's the reason. You can only do 128 concurrent invocations. When you first time you invoke a record UDF, you get 10 states in the memory. So 9 other clients can use it. More come, then we'll create up to 128. After that, it gets instantiated on the heap. And that just starts sucking. Okay? So that's why. It'll still work. It'll just, if you're okay with performance, and if you don't expect more than 128 concurrent invocations, go ahead, use UDFs. That's the only time it starts sucking, if you have more than 128 clients trying to use the same UDF on the same node. You can make a copy of the UDF and call it different names, and then each of them will get 128 buckets, right? If you want to do that level of complexity in your application, sure. All right, so let me quickly go through transaction flow. So how the read transactions work inside Aerospike. And the reason I'm bringing it is for you to understand that all the latency comes really when we go on the fabric. Now, typically a read transaction, once we get it from the receive card, NIC receive channel, we'll take it, let's say if it's data in memory or in device, either way, it'll come and we'll do a read local unless we have to do duplicate resolution. That only happens during migrations, right? And that also, if you have asked for it, right? So but in case of strong consistency mode, if you do globally linearized reads, then we have to do the replication pinging to each node. So when you do that, you have to go on the fabric. That slows down your reads. If you're not doing, SC mode globally linearized reads, then you're going to straight go into reading the data. Okay? So by default, there is no duplicate resolution in reads. If you turn that on, you're going to pay a price in read latency. So I want to point that out. If you're worried about latency, and then you're going to get your transaction and off you go. Okay? Now, we also have read page cache that was introduced last year. So if you're writing to device, you can turn on the caching of the reads, so that if you read a record, and if you're doing hotkey reads, if you're reading the same key again and again, then it'll be served from the cache itself. But obviously, if the key is updated, the cache will be marked dirty, and then it'll go back to the device and fetch it. So you won't get any inconsistency, you'll just get performance for hotkeys. So consider that if you have hotkeys. Now let's quickly look at the write transaction flow. A typical write will replicate, right? So right off the bat, we put the transaction into what we call a read-write hash, which is where the transactions basically are picked from and sent on the fabric for replication, right? Now, writes always do duplicate resolution as well, if required. So let's assume migrations are not going on, we're not going in this phase, and we are ready to do a local write. So the local write will happen very fast because it only goes to the write block buffer in RAM. So that's a fast operation. Where do you lose time is when you go for replicas and you wait for the answer. So you have an option in the write policy to say, hey, don't wait for the replica answer. Just send it to the replica and I don't care. That's called fire and forget. You go there, you'll get your write response right away. So you can speed up your writes very fast if you don't care for replica response. So I wanted to point that out. What are the implications for that? Well, if you do, you can do it as a namespace configuration. Don't recommend that because then every record becomes a fire and forget. You should do it via write policy for every record you're writing, so you have control over it, right? You're not going to wait, and you should monitor the RAM usage. In this case, if you're going to use fire and forget for this buffer piling up, because now you're just firing away and going, firing away and going. If you have very high traffic, this buffer will start piling up in RAM. So keep an eye on that. The other thing you want to do is, data modeling wise, hey, should I use fire and forget? So my question to you is, in your current data model, do you handle timeouts? Well, if you're not handling timeouts, which is primarily comes from the fabric being slow for one reason or the other, if you're not handling timeouts, quite likely you can use fire and forget. Okay? Now, if you're not handling timeouts because you forgot to, that's a different issue. But by design, if you say, I don't need timeouts, then you are a good candidate for fire and forget. If your design is robust enough or whatever you're doing doesn't need timeout handling, then consider fire and forget. It is pretty neat. And now you can ask questions.
With fire and forget,
yes.
will it eventually replicate?
Yeah, it will replicate. You just don't wait for the ACK. So you're avoiding that delay on the fabric. Because, this fabric transmit, and it'll wait for the receive, and then it goes to the response in a normal case. In fire and forget, you bypass that. You still do the transmit, you just don't wait for the ACK.
It could cause inconsistency though, right?
Exactly. It's an AP mode deal only. You can't do this in SC, by the way. In strong consistency, this is not possible. It has to meet your data model requirements. So
multi-record, you said you can lock the record and come back, do the process, come back. So during that time, if the client dies, how that get cleared?
So other clients, that's why I said, either you have to poll, you have to assign a time, right? That I will only be good for so long. Yeah, so you're doing that all yourself. You're putting an expiration time here. Okay, and then everybody goes, oh, looks like this guy just abandoned. You should have been done in 100 milliseconds, and you can be generous, put 500 milliseconds. Say, I'm 5x giving myself headroom. This is definitely an abandoned situation. So, well, you are writing the application, right? So, right, so then others will unwind. And you're only copying the data. So regardless of where you fail, you're not going to pollute it. This is append only, right? If you're going to update the data, then you have to go to my previous model, where you are maintaining state. Then you can unwind with state. You have to make the record fully stateful. But these are all application level tricks. And the adaptive map is a good place to start if you have something like this in mind to see how it is done. It's a fairly extensive code. Any others?
On page 31, go back to 31. If you go back to page 31, I think it was the previous slide. Further. It's the one with the tree where you delete the note. You create this one here. It looks like what you described the algorithm is like a self-balancing tree. So you delete record 2 when, say, record 3 has record 5, your record.
No, it's nothing, it's self-splitting.
Self-splitting.
So this had data, and when I wrote the last